The space between two people who love each other grows by about 3 centimeters every year, not through argument or neglect, but through the quiet expansion of everything that exists. This is not tragedy. It is the nature of a universe still stretching outward from its first breath, carrying all matter gently apart, including the atoms that make up hands once held, voices once familiar, hearts once certain of their closeness. If these slow reflections bring rest, a subscription ensures more will find their way to you in time. What follows is a story about distance, the kind measured in light years and the kind measured in unanswered messages, in holidays grown quieter, in the soft fade of faces we swore we would never forget. Both obey the same ancient law, and both carry their own strange mercy. And so we begin here, drifting. On a warm summer evening, when the air has finally released the heat of the day and settled into something softer, you might find yourself lying on your back in the grass, perhaps in a garden or a quiet field somewhere away from the bright insistence of street lamps, and as you lie there with the cool earth pressing gently against your shoulders and the faint smell of green things growing all around you, you may notice that your breathing has slowed and your thoughts have begun to drift upward, following your gaze into the darkening sky above, where the first stars are beginning to appear one by one, like small, careful punctuation marks in the vast sentence of the evening. And in this moment, as the constellations gradually reveal themselves in patterns that seem at once random and deeply familiar, you might feel something that humans have felt for as long as we have had eyes to look upward and minds to wonder, which is a sense of profound stillness, a quiet certainty that you are looking at something permanent, something that was here long before you arrived and will remain long after you have gone, watching over the world with the patient indifference of eternity itself. This feeling of cosmic permanence has been with us for a very long time indeed, woven so deeply into the fabric of human experience that we rarely think to question it. And when you consider how the night sky must have appeared to the earliest humans who craned their necks to study those distant points of light, you can begin to understand why this assumption of stillness became so firmly established in our collective understanding of the universe. Because the stars truly do seem fixed in place, rotating overhead in their stately nightly procession, but never changing their positions relative to one another. The same patterns appearing night after night and season after season. So reliable in their constancy that ancient civilizations built entire calendars and navigation systems and religious cosmologies around the reassuring predictability of their arrangement. And this is not a foolish assumption by any means, because it is based on careful observation of the evidence available to the naked eye, which is all that humans had for most of our history. In the year 129 before the Common Era, on the island of Rhodes in the warm waters of the eastern Mediterranean, a Greek astronomer named Hipparchus undertook a remarkable project that would occupy him for many years and establish his reputation as one of the greatest observers of the ancient world. And this project was nothing less than a comprehensive catalogue of the stars, a systematic attempt to record the position and brightness of every visible star in the night sky, so that future generations might have a reliable reference for their own observations. And when Hipparchus finally completed this monumental work, he had documented approximately 850 stars, each one carefully measured and recorded, each one assigned to its proper place in the celestial sphere. And the implicit assumption underlying this entire enterprise was that these stars would remain exactly where he had charted them, not just for the next decade or century, but forever, because the stars were understood to be fixed, permanent, unchanging features of the cosmos, as eternal and immutable as the gods themselves. The very language that ancient peoples used to describe the sky reveals how deeply this assumption of permanence shaped their thinking. And perhaps the most telling example is the word firmament, which appears in many religious and philosophical texts from the ancient world, including the opening passages of the Hebrew Bible, where it describes the structure of the heavens. And the etymology of this word is quite illuminating, because it derives from the Latin word firmamentum, which in turn comes from the verb firmare, meaning to make firm, or to strengthen, or to establish securely. And this word was itself a translation of the Greek word stereoma, which carried connotations of solidity and rigidity, suggesting something hard and fixed and unyielding. And so, when ancient peoples spoke of the firmament, they were not using a vague poetic term, but rather expressing a specific understanding of the cosmos as a solid structure, a crystalline dome or sphere in which the stars were embedded like jewels set permanently into the surface of a great revolving bowl. And this understanding persisted in various forms for thousands of years, shaping how countless generations thought about their place in the universe. If you could somehow travel backward through time to visit your grandmother as a young woman, perhaps sitting on a porch on a summer evening much like this one, watching the same stars emerge from the darkening sky, you would find that the constellations she observed were essentially identical to the ones you see tonight. Orion striding across the winter sky with his belt of 3 bright stars, the Big Dipper wheeling slowly around Polaris, the Pleiades clustering together in their distinctive grouping, all of them appearing exactly as they appeared to her. And if you could travel further back still to find her grandmother, your great-great-grandmother, watching the sky from whatever part of the world she called home, you would find the same constellations waiting for her as well, unchanged and unchanging, a constant backdrop to the brief dramas of human life. And this continuity across generations creates a powerful impression of stability, a sense that whatever else may change in this world of impermanence and loss, the stars at least can be relied upon to remain where they have always been. Consider Polaris, the North Star, which has served as a guide for travelers and navigators for thousands of years, providing a fixed point of reference in the northern sky around which all the other stars appear to rotate. And countless sailors have set their course by this star, trusting it to show them the direction of true north when all other landmarks had disappeared below the horizon. And shepherds watching their flocks by night have used it to orient themselves, and travelers crossing unfamiliar territory have followed it like a beacon. And the very fact that we call it a fixed star reflects our deep assumption that it occupies a permanent and unchanging position in the heavens, reliable across centuries and millennia. A cosmic constant in a universe that can sometimes seem bewildering in its complexity. And there is something genuinely comforting in this idea, something that settles the mind and eases the spirit. The thought that at least this one thing in all the universe can be counted upon to remain where it is. This intuitive sense of cosmic permanence is not limited to ancient peoples or to those who spend their evenings stargazing, because even today, In an age of sophisticated telescopes and space probes and detailed maps of distant galaxies, most people carry within them an assumption that the large-scale structure of the universe is essentially static, that the galaxies and stars occupy fixed positions in space and have always done so, much as the furniture in your home occupies fixed positions in your living room. And surveys of public understanding of astronomy have revealed just how widespread this assumption is. Because when researchers asked people about their beliefs regarding the cosmos, they found that roughly 2/3 of Americans, according to a survey conducted in 2015, believed that galaxies remain in fixed positions relative to one another, not moving closer together or farther apart, but simply existing in their assigned places in the great scheme of things. And this is a perfectly understandable belief, because it matches our everyday experience and the evidence of our senses. And there is no reason why anyone without specialized training in cosmology should think otherwise. After all, when you look up at the night sky tonight, it appears identical to the sky you observed last month, or last year, or 10 years ago. And there is no visible indication that anything is moving on a cosmic scale. No obvious sign that the universe is anything other than the stable and unchanging place it appears to be. And this is because the motions that are occurring, the vast migrations of matter through space, happen on scales so enormous and over timescales so inconceivably long that they are utterly invisible to human perception, like trying to watch a glacier flow by staring at it for an afternoon, or trying to observe the erosion of a mountain by glancing at it once a decade. And so our intuition tells us that the universe is still, and our intuition feels completely reliable, because it is based on a lifetime of observation, and our parents' lifetimes of observation, and their parents' lifetimes stretching back through the generations. And none of these accumulated observations have ever suggested otherwise. But here is where things become interesting. And I use that word advisedly, because there is a quiet kind of interest in discovering that something you have always believed to be true turns out to contain a fundamental misunderstanding. Not a small error that can be easily corrected, but a profound inversion of reality that requires you to reconceive your entire picture of the cosmos. And this is precisely what happened in the late 1920s, in the hills above the city of Los Angeles, at a place called the Mount Wilson Observatory, where a man named Edwin Hubble was about to make a discovery that would shatter the ancient assumption of cosmic stillness as completely and irreversibly as anything has ever been shattered in the history of human thought. Hubble was working with the Hooker telescope, which at that time was the largest telescope in the world, with a mirror 100 inches in diameter that gathered light from impossibly distant sources and focused it for human study. And Hubble had been observing what were then called spiral nebulae, fuzzy patches of light that some astronomers believed were clouds of gas within our own galaxy, and others suspected might be entire galaxies in their own right. And through painstaking observation and careful analysis, Hubble had already established that at least some of these nebulae were indeed separate galaxies, what he called island universes, lying at distances so vast that the light from them had been traveling for millions of years before it reached his eye. And this alone was a remarkable enough discovery, expanding the known universe from a single galaxy to a cosmos containing millions or perhaps billions of these great star cities. But what Hubble observed next was something far more unsettling. something that would require not just an expansion of our map of the universe, but a complete revision of our understanding of its fundamental nature. And in 1929, after carefully studying the light from dozens of these distant galaxies and comparing his observations with those of other astronomers, Hubble announced his findings to the world. And these findings contained within them a truth so strange and so contrary to common intuition that it would take decades for its full implications to be absorbed. And even now, nearly a century later, many people remain unaware of it or struggle to grasp its meaning, because it tells us that the universe is not what it appears to be, that the stillness of a summer evening is an illusion, that the fixedness of the stars is a trick of perspective and timescale, and that everything, absolutely everything, is in motion in ways that we cannot directly perceive. And yet, this truth has been traveling toward us all along, encoded in the light that reaches your eyes whenever you look up at the night sky. Because light is not merely illumination, not simply a way of seeing distant objects, but also a messenger carrying information about its source. And the light from distant galaxies has been journeying across the void of space for millions or even billions of years, crossing incomprehensible distances at the fastest speed the universe allows. And during all that time, it has carried within it a subtle signature, a delicate shift in its properties that reveals something profound about the nature of the cosmos. And this signature was there all along, waiting to be read by anyone who knew how to look for it. And when Hubble and others finally learned to decipher this message, they found that it contained an unsettling secret, a truth that would transform our understanding of the universe and our place within it. Tonight, as you lie on your back in the grass and watch the stars slowly wheeling overhead, light is falling on your eyes from sources scattered across the observable universe, some of it from relatively nearby stars within our own galaxy, and some of it from galaxies so distant that they appear as nothing more than faint smudges even through the most powerful telescopes. And all of this light, every photon that strikes your retina and triggers the cascade of signals that allows you to see, carries within it information about its journey, and some of that information concerns the way the universe has been changing during the millions or billions of years that light has been traveling. And the story this light tells is not the story of permanence and stillness that the summer evening seems to promise, but rather a story of motion and change and a cosmos that is fundamentally different from the one our ancestors imagined when they first looked up at the heavens and named the constellations after their gods and heroes. In the high desert of northern Arizona, where the air is thin and the nights are very cold and very still, there stands an observatory on a mesa called Mars Hill. The year is 1912. And a young astronomer named Vesto Melvin Slipher is beginning a project that will take him years to complete. Though he does not know this yet, and he does not know that the measurements he is about to make will eventually change everything we believe about the universe and our place within it. He is 37 years old, and he has been working at Lowell Observatory for more than a decade. Hired originally by the observatory's founder, Percival Lowell, to study the planets, particularly Mars, which Lowell believed showed evidence of canals built by intelligent beings. But Slipher has been given a new assignment now, one that seems rather modest at the time, which is to point the observatory's 24-inch refracting telescope at certain fuzzy patches of light in the night sky. objects that astronomers of the era call spiral nebulae, and to determine what these curious smudges are made of by analyzing the light they emit. The telescope on Mars Hill is a good one, though not the largest in the world, and Slipher has fitted it with a device called a spectrograph, which takes incoming light and spreads it out into its component colors, much as a prism spreads sunlight into a rainbow. When you do this to the light from a star or a nebula, you do not simply see a smooth band of colors running from red to violet, but rather you see dark lines crossing the spectrum at very specific positions, and these lines are like fingerprints, because each chemical element absorbs light at particular wavelengths and leaves its own distinctive pattern of shadows in the rainbow. By examining these absorption lines, an astronomer can determine what elements are present in a distant object without ever traveling there, which is rather convenient given that travel to such places is quite impossible. Slipher had become expert at this technique over his years at Lowell, and so it fell to him to turn this method upon the spiral nebulae and see what secrets their light might reveal. But there was a difficulty, and it was a considerable one, which is that spiral nebulae are exceedingly faint, much fainter than the stars that surround them, and to capture enough of their light to produce a useful spectrum required Slipher to keep the photographic plate exposed for extraordinarily long periods of time. We are not speaking of minutes here, nor even of a few hours, but rather of exposures that stretched across 20, 30, sometimes 40 hours of total observation time, accumulated over the course of multiple nights, because even the longest winter night cannot provide 40 continuous hours of darkness. During each of these observing sessions, Slipher had to keep the telescope pointed precisely at the same tiny patch of sky, compensating constantly for the rotation of the Earth, which tries always to carry the stars across the field of view. He did this work largely alone, in the cold and the silence of the Arizona night, with only the slow clockwork of the telescope drive and the distant coyotes for company. When Slipher finally developed his photographic plates and examined the spectra he had captured, he noticed something peculiar, something that at first must have seemed like a mistake or an artifact of his equipment. The dark absorption lines in the spectrum of the Andromeda Nebula, that great spiral visible to the naked eye on clear autumn evenings, were not in quite the positions where he expected them to be. They were shifted slightly from their normal wavelengths, displaced toward the blue end of the spectrum, which indicated that the Andromeda Nebula was moving toward us at a speed of approximately 300 kilometers per second. This was an enormous velocity, far greater than the typical motions of stars within our own Milky Way, and it was interesting enough on its own. But what came next was far more interesting still. As Slipher continued his patient observations through 1913 and 1914 and the years that followed, measuring the spectra of one spiral nebula after another, he began to see a pattern emerging from his data that was both unexpected and difficult to explain. Most of the spiral nebulae did not show a blue shift like Andromeda, but rather a redshift, meaning their absorption lines were displaced toward the red end of the spectrum, toward the longer wavelengths of light. And a red shift means motion away from us, recession into the depths of space, as though these nebulae were fleeing the Milky Way for reasons no one could fathom. By 1917, Slipher had measured the spectra of 41 spiral nebulae, and of these, 36 showed red shifts. Only 4, including Andromeda and a few of its neighbors, were approaching. The rest were receding, some of them at speeds that seemed almost unbelievable at the time. Velocities of 500, 800, even 1100 kilometers per second, which is to say nearly 4 million kilometers per hour, which is to say very fast indeed by any earthly standard, though still only a tiny fraction of the speed of light. To understand why the color of light tells us about motion, we must travel back in time a bit further, to the city of Prague in 1842, where a mathematician and physicist named Christian Johann Doppler was thinking about waves. Doppler realized that when a source of waves is moving toward you, the waves become compressed, squeezed together so that more wave crests reach you each second than would arrive from a stationary source. And this compression corresponds to a higher frequency and, in the case of sound, a higher pitch. Conversely, when a source of waves is moving away from you, the waves become stretched out, elongated, so that fewer wave crests arrive each second, corresponding to a lower frequency and a lower pitch. You have experienced this effect many times in your life without perhaps knowing its name, because it is what makes the siren of an ambulance or a fire truck change pitch as the vehicle passes you on the street. As the ambulance approaches, the siren sounds higher, and as it recedes into the distance behind you, the siren drops to a lower tone. And this change happens precisely at the moment the ambulance passes closest to you and begins to move away rather than toward. Doppler understood that this effect should apply to light as well as to sound, because light, too, is a wave phenomenon. And if a source of light is moving toward you, its waves should be compressed and shifted toward the blue end of the spectrum, where the wavelengths are shorter, while if a source of light is moving away from you, its waves should be stretched and shifted toward the red end of the spectrum, where the wavelengths are longer. This is exactly what Slipher was observing in the spectra of the spiral nebulae, and the amount of the shift told him how fast they were moving, and the direction of the shift, whether toward blue or toward red, told him whether they were approaching or receding. The mathematics of this relationship is straightforward enough that Slipher could calculate velocities from his measurements with considerable confidence. And what the numbers told him was that nearly all of these spiral nebulae were rushing away from the Milky Way at tremendous speeds, as though something had frightened them, as though they wanted nothing to do with us. In February of 1914, Slipher traveled from Flagstaff to Evanston, Illinois, to present his findings at a meeting of the American Astronomical Society, and when he finished describing his observations and the velocities he had measured, something unusual happened, something that almost never occurs at scientific meetings, which tend to be rather subdued affairs characterized by polite applause and technical questions. The assembled astronomers rose to their feet and gave Slipher a standing ovation. They recognized that he had discovered something remarkable, even if they did not yet understand what it meant, even if the full implications of his measurements would not become clear for another 15 years. Slipher was not given to self-promotion or dramatic announcements, and he returned to his quiet work at Lowell Observatory, continuing to measure spectra, continuing to add to his catalogue of recession velocities, content to let the data speak for itself in due time. What no one understood yet, including Slipher himself, was that the spiral nebulae were not nebulae at all, not clouds of gas within our own Milky Way, but rather entire galaxies in their own right. Vast collections of hundreds of billions of stars lying at distances so great that the light reaching Slipher's telescope had been traveling for millions of years before arriving at his photographic plates. The Milky Way was not the whole of the universe, as most astronomers of the time assumed, but merely one galaxy among countless others. And these other galaxies were scattered throughout a cosmos far larger than anyone had imagined. This realization would not come until 1924, when Edwin Hubble, working with a much larger telescope on a mountain in California, identified individual stars in the Andromeda Nebula and proved that it lay far beyond the boundaries of the Milky Way. But even without this knowledge, Slipher had already provided the crucial observation, the first whisper from the light itself, telling us that something very strange was happening on the largest scales, that the contents of the universe were in motion, and that this motion had a peculiar one-sidedness to it, a preponderance of recession over approach that demanded explanation. Meanwhile, in Berlin, a physicist named Albert Einstein was wrestling with the implications of his own theory of general relativity, which he had completed in 1915 and which described gravity not as a force in the traditional sense, but as the curvature of space and time caused by the presence of mass and energy. When Einstein applied his equations to the universe as a whole, he found something troubling, which is that they did not permit a static solution, a universe that simply sat there, unchanging for all eternity. According to the mathematics of general relativity, a universe filled with matter should either be expanding or contracting, growing larger with time or collapsing in upon itself, but it should not be standing still. This bothered Einstein greatly because, like nearly everyone else in 1917, he believed that the universe was eternal and unchanging, that it had always existed in more or less its present state and would continue to exist in that state forever. The idea of a universe with a beginning or an end, or a history of cosmic evolution, seemed philosophically unacceptable to him, and so he modified his equations by adding a term that he called the cosmological constant, a kind of repulsive pressure built into the fabric of space itself, precisely calibrated to counteract the attractive force of gravity and hold the universe in perfect balance, neither expanding nor contracting, but hovering eternally at the same size. Einstein later called this modification the biggest blunder of his career, because he had been handed a prediction from his own theory, a prediction of exactly the kind of cosmic expansion that Slipher was beginning to detect, and he had refused to accept it, choosing instead to preserve his preconceptions about how the universe ought to behave. But that is the wisdom of hindsight. And in 1917, no one yet realized that Slipher's red shifts were evidence of cosmic expansion, that the spiral nebulae were receding not because they were moving through space in the ordinary sense, but because space itself was stretching between them, carrying them apart the way dots on the surface of an inflating balloon move apart, even though no force is pushing them. That understanding would come later, after Hubble measured the distances to the spiral galaxies, after Georges Lemaitre and others worked out the theoretical framework, after the accumulated evidence became too overwhelming to ignore. But Slipher was the first witness, the quiet observer who recorded the data without fully grasping its meaning, who spent countless cold nights alone on Mars Hill, gathering the light of distant galaxies and teasing out the subtle shifts in their spectral lines that told of motion and recession and a universe in flight from itself. The standing ovation at the American Astronomical Society was a recognition of his skill and his dedication and the significance of his observations. But it was also, in a sense, a farewell to the old static universe, though no one knew it at the time. The first whispers from the light had been heard, and they were telling us something that would prove very difficult to accept, which is that the universe is not standing still, that everything is drifting away from everything else, and that this drifting cannot be stopped by any force known to physics, because it is not motion through space, but the expansion of space itself, carrying galaxies and clusters and all the structures of the cosmos gently and inexorably apart. In the early years of the 20th century, at the Harvard College Observatory in Massachusetts, there worked a group of women who were given the official title of computers, for their job was to compute, to measure, to catalogue, and to perform the painstaking mathematical work that the male astronomers of the time considered too tedious for their own attention. These women were paid 30 cents per hour, which was considered reasonable compensation for work that required extraordinary patience, meticulous eyesight, and a tolerance for spending one's days in rooms filled with thousands upon thousands of glass photographic plates, each one containing a small rectangular window into the night sky. Among these women was Henrietta Swan Leavitt, who had graduated from what would become Radcliffe College and who had, despite being profoundly deaf, developed an exceptional ability to notice the subtle variations in the brightness of stars as they appeared across multiple photographs taken on different nights. The photographic plates that Henrietta Leavitt studied had been exposed at Harvard's observing station in Arequipa, Peru, where the southern skies revealed celestial objects that could not be seen from the northern hemisphere, and among these objects were the Magellanic Clouds, which appeared to the naked eye as faint, hazy patches of light, but which resolved under the telescope into dense congregations of individual stars. Miss Leavitt, as she was formally addressed in the observatory records, had been assigned the task of identifying variable stars within these clouds, which is to say, stars whose brightness changed over time in a regular and repeating pattern. And over the course of several years, she catalogued more than 2,000 of these pulsating stars, recording their periods of variation with extraordinary care. The work was slow, for each measurement required comparing the same star across dozens of different plates, noting how its brightness waxed and waned over days or weeks, and then calculating precisely how long each cycle of brightening and dimming required. By 1908, Henrietta Leavitt had begun to notice something peculiar about a particular class of variable stars known as Cepheus, named after the prototype star Delta Cepi in the northern constellation Cepheus, and what she noticed was that the brighter Cepheid variables seemed to pulse more slowly than the fainter ones. This might seem, at first consideration, to be an unremarkable observation. For one might assume that the brighter stars were simply closer to us and therefore appeared more luminous. But Miss Leavitt recognized something that many others had overlooked. which was that all of the Cepheid variables she was studying resided within the same Magellanic Cloud. And because this cloud was so extraordinarily distant, all of its stars could be treated as being effectively the same distance from Earth. This meant that the differences in apparent brightness among these Cepheids were not due to differences in distance, but rather to genuine differences in their intrinsic luminosity, their actual light output. And if the brighter stars truly pulsed more slowly, then there existed a direct mathematical relationship between how luminous a Cepheid actually was and how long it took to complete one cycle of variation. In 1912, Henrietta Leavitt published her findings in a brief paper in the Harvard College Observatory Circular, presenting what would come to be known as the period luminosity relationship. And, though the paper carried the name of the observatory director, Edward Pickering, as its author, with Miss Leavitt credited only in the acknowledgements, the discovery was entirely her own. What she had found was nothing less than a cosmic measuring tool, a standard candle that could reveal the true distances to objects far beyond what any previous method could reach. For if one could observe a Cepheid variable anywhere in the universe and measure how long its pulsation cycle lasted, one could immediately determine how intrinsically luminous that star must be. And by comparing that intrinsic luminosity to how bright the star appeared from Earth, one could calculate precisely how far away it was. The mathematics of this were straightforward, following from the simple principle that light dims predictably with distance, spreading out across space according to an inverse square relationship that had been understood since the time of Johannes Kepler. Henrietta Leavitt did not live to see the full implications of her discovery, for she died in 1921 at the age of 53. And it was left to others to take her cosmic yardstick and apply it to the deepest questions of astronomy, questions about the true scale of the universe and whether the hazy spiral nebulae that dotted the sky were merely local clouds of gas within our own galaxy, or whether they were, as some had long suspected, entire galaxies in their own right, island universes separated from our Milky Way by almost unimaginable gulfs of emptiness. This question had become the subject of intense debate among astronomers, and in April of 1920, the Smithsonian Institution in Washington hosted what would later be called the Great Debate, a formal discussion between two distinguished astronomers who held opposing views on the matter of the spiral nebulae and the size of the cosmos. On one side of this debate stood Harlow Shapley, who had recently used observations of globular star clusters to demonstrate that the Milky Way galaxy was far larger than previously believed, extending perhaps 300,000 light-years from edge to edge. And Shapley argued that this vast galaxy was essentially the entire universe, with the spiral nebulae being relatively small and nearby objects, perhaps condensing clouds of gas that would eventually form new solar systems. On the other side stood Heber Curtis of the Lick Observatory in California, who believed that the spiral nebulae were external galaxies, each one comparable in size to our own Milky Way and located at distances of millions of light-years, which would make the universe incomprehensibly larger than Shapley's already enormous conception. The debate itself resolved nothing, for neither astronomer possessed the observational evidence that would settle the matter definitively, and both men returned to their respective institutions, no more persuaded than they had been before. But the question lingered in the minds of astronomers everywhere. waiting for the technology and the observations that could provide an answer. That answer began to emerge on the night of October 6, 1923, when a young astronomer named Edwin Hubble sat in the observer's cage of the 100-inch Hooker telescope on Mount Wilson in the mountains above Pasadena, California, which was at that time the largest and most powerful telescope ever constructed. Hubble had been photographing the Great Spiral Nebula in Andromeda, known in the star catalogues as Messier 31 or simply M31. And on this particular night, he obtained an exposure that, when developed and examined, revealed what appeared to be a nova, a star that had suddenly brightened within the nebula's spiral arms. Hubble marked this object on the photographic plate with the letter N, as was customary for novae, and set the plate aside for further study. But when he compared his new photograph with older plates of the same region, he discovered something that made him cross out the N with evident excitement and write instead the letters VAR, for variable. The object he had found was not a nova at all, but a Cepheid variable star, pulsing with a regular period of approximately 31 days. And because Henrietta Leavitt had established the relationship between a Cepheid's period and its intrinsic luminosity, Hubble could now perform a calculation that no one had been able to perform before. He knew how bright this star actually was, based on its pulsation period, and he knew how bright it appeared in his photographs, and from these two numbers he could determine the distance to the star and therefore to the Andromeda Nebula in which it resided. The result of his calculation was staggering, for it indicated that the Andromeda Nebula was approximately 900,000 light-years from Earth, which placed it far, far beyond the boundaries of even Shapley's greatly expanded Milky Way galaxy. The spiral nebulae were not local objects at all, but were instead separate galaxies, vast collections of hundreds of billions of stars. And the universe was suddenly immensely larger than anyone had dared to imagine. We now know that Hubble's original distance estimate was too small by a factor of nearly 3, for there were complications in the Cepheid relationship that were not yet understood in 1923, and the true distance to the Andromeda Galaxy is approximately 2.5 million light-years. But even Hubble's underestimate was sufficient to demolish forever the notion that our galaxy was the entirety of the cosmos. Hubble published his findings in January of 1925, presenting them at a meeting of the American Astronomical Society. And, though Harlow Shapley reportedly said upon hearing the news that this letter had destroyed his universe, the astronomical community quickly accepted the evidence, for the observations were careful and the mathematics were sound. The Cepheid variable that Hubble had discovered, now designated V1, still pulses quietly in its distant galaxy, and it has been observed many times since with increasingly sophisticated instruments, most recently with the Hubble Space Telescope, which bears the name of the man who first recognized its significance. But the distances themselves, however breathtaking, were only the beginning of what the new telescopes would reveal. For even as Hubble was measuring how far away the external galaxies were, another astronomer had been measuring something equally important, which was how fast those galaxies were moving. Vesto Slipher, working at the Lowell Observatory in Arizona, had spent more than a decade carefully measuring the spectra of spiral nebulae, spreading their light into its component wavelengths and noting the precise positions of the dark absorption lines that appeared wherever particular elements had absorbed specific frequencies of light. What Slipher discovered was that these spectral lines were almost always shifted toward the red end of the spectrum, stretched to longer wavelengths in a manner that indicated the nebulae were moving away from us at remarkable velocities, some of them receding at speeds of hundreds or even thousands of kilometers per second. This phenomenon, known as the redshift, was well understood from laboratory physics. For when a source of light is moving away from an observer, the waves of light become stretched out and shifted toward the red, just as the sound of a receding ambulance siren drops to a lower pitch. And Slipher's observations left little doubt that the spiral nebulae, whatever they might be, were almost universally rushing away from Earth. By 1917, Slipher had measured the redshifts of 25 nebulae and found that 21 of them were receding, with only 4 approaching, and though he did not yet know the distances to these objects, he suspected that something profound was happening on a cosmic scale. It was Edwin Hubble who brought together the 2 threads of evidence, combining his own distance measurements with Slipher's velocity measurements. And in 1929, he published a paper that would transform humanity's understanding of the universe. What Hubble found was that the recession velocities of the galaxies were not random, but were instead proportional to their distances, so that a galaxy twice as far away was receding twice as fast, and a galaxy 10 times as far away was receding 10 times as fast. This proportional relationship, which would come to be known as Hubble's law, had a startling implication, for it meant that the entire universe was expanding, that the fabric of space itself was stretching and carrying the galaxies along with it, and that the farther away an object was, the more space there was between it and us, and therefore the faster that space was carrying it away. Yet history, in its unhurried way, would eventually reveal that Hubble was not the first to recognize this expansion. In 1927, 2 years before Hubble's famous paper, a Belgian priest and physicist named Georges Lemaitre had published an article in an obscure French-language journal called the Annales de la Société Scientifique de Bruxelles, in which he derived the theoretical relationship between distance and recession velocity from Einstein's equations of general relativity, and then demonstrated that the available observational data supported this relationship. Lemaitre, who had studied at Cambridge and at the Massachusetts Institute of Technology, understood both the mathematics of relativity and the practicalities of astronomical observation, and his paper contained essentially everything that Hubble would later publish, including an estimate of the proportionality constant that was remarkably similar to Hubble's own value. But Lemaitre's paper went largely unnoticed by the astronomical community, published as it was in a journal that few astronomers read, written in a language that many did not speak, and presenting conclusions that seemed, at the time, almost too radical to accept. When the paper was later translated into English in 1931, the passages containing Lemaitre's original estimate of the expansion rate were mysteriously omitted, and for decades historians assumed that this omission was the work of editors who wished to preserve Hubble's priority, though it was eventually discovered that Lemaitre himself had removed these passages, perhaps out of modesty, perhaps because he felt that Hubble's more recent and more accurate data had superseded his earlier estimates. Whatever the reason, the expansion of the universe became associated primarily with Hubble's name. And it is only in recent years that astronomers have begun to refer to the Hubble-Lemaitre law in recognition of the Belgian priest's independent and earlier discovery. The universe that emerged from these observations and calculations was something entirely new in human thought. A cosmos that was not static and eternal, but dynamic and evolving. A vast expanse of space that was itself growing larger with each passing moment. The galaxies were not flying apart through a pre-existing emptiness, but were instead being carried along by the expansion of space itself, like raisins in a rising loaf of bread, each one moving away from every other one as the dough between them swells. And because this expansion was proportional to distance, there was no center to the universe, no special point from which everything was fleeing, for an observer in any galaxy would see precisely the same pattern that we see from Earth, with all other galaxies receding at speeds proportional to their distances. The universe was not just vast, as generations of astronomers had gradually come to understand. The universe was growing. Let us begin with something that may seem, at first, rather counterintuitive, though once you settle into the idea, it becomes strangely comforting in its simplicity. When we speak of the universe expanding, of galaxies drifting apart from one another across the vast and quiet reaches of cosmic space, we are not describing motion in the way you might ordinarily think of it. The galaxies are not, as it were, flying through space like birds migrating across an autumn sky, nor are they rushing away from us as though fleeing some great cosmic disturbance at the center of things. No, the truth is rather more subtle than that, and rather more peculiar, and it has to do with the very fabric of space itself, which is, as we shall see, not a fixed and immutable stage upon which the drama of the universe unfolds, but something altogether more dynamic, something that stretches and grows in the quiet intervals between all things. To understand this, it may help to consider an analogy that has been attributed, in various forms, to the British astronomer and physicist Sir Arthur Eddington, who was himself a great popularizer of scientific ideas in the early 20th century, and who played no small role in confirming certain predictions of Albert Einstein's theories. Eddington invited his readers to imagine a loaf of raisin bread, the sort you might find in a modest bakery, studded throughout with raisins suspended in the soft dough. Now, imagine that this loaf is placed in the oven to bake, and as the heat penetrates the dough, the bread begins to rise. The dough expands, swelling outward in all directions, and as it does so, something interesting happens to the raisins. Each raisin, from its own point of view, sees all the other raisins moving away from it. The raisins themselves are not crawling through the dough. They are not propelling themselves by any internal mechanism. They are simply being carried along as the dough between them stretches and grows. A raisin near the center of the loaf sees raisins moving away in every direction, and a raisin near the edge sees exactly the same thing, for there is no true center to the expansion, no privileged location from which the swelling originates. The expansion is happening everywhere at once, in the spaces between all the raisins, and each raisin, if it could think, would conclude that it was the center of a great cosmic exodus. This, in essence, is what is happening to our universe, Though of course the universe is not made of dough and the galaxies are not raisins. And the whole affair is taking place across distances so vast that the human mind can only gesture toward them with numbers that have little intuitive meaning. The galaxies are embedded in the fabric of space-time, and it is this fabric that is stretching, carrying the galaxies along with it. The space between the galaxies is growing, not because the galaxies are moving through space, but because there is, in a very real sense, more space coming into existence all the time. This is a strange idea, perhaps, but it is one that emerges quite naturally from the mathematics of modern cosmology, and it is supported by an overwhelming weight of observational evidence that has accumulated over the past century. The theoretical foundation for this understanding was laid in the year 1915, when Albert Einstein published his general theory of relativity, a monumental work that reimagined gravity not as a force acting at a distance, in the manner of Isaac Newton, but as a consequence of the curvature of space-time itself. In Einstein's theory, massive objects like stars and planets warp the geometry of the space around them, and other objects moving through this warped space follow paths that we perceive as the effects of gravitational attraction. The equations that Einstein wrote down, known as the field equations of general relativity, are extraordinarily rich in their implications, and they describe not only the behavior of objects within the universe, but also the behavior of the universe as a whole. When one applies these equations to the cosmos, treating the universe as a vast and roughly uniform distribution of matter and energy, one finds that the equations do not naturally admit a static solution. The universe described by general relativity is, in a sense, restless. It wants to either expand or contract. It does not wish to sit still. Einstein himself was troubled by this implication. In 1915, and for some years afterward, the prevailing view among astronomers was that the universe was static and eternal, a fixed arena that had always existed and would always exist in more or less its present form. To reconcile his equations with this assumption, Einstein introduced an additional term, a kind of cosmic fudge factor, which he called the cosmological constant. This term acted as a sort of repulsive force, pushing against the tendency of gravity to pull matter together, and it allowed for a static universe in which expansion and contraction were held in perfect balance. Einstein was not entirely happy with this addition, for it seemed rather ad hoc, rather inelegant, but he saw no alternative at the time. It was a young Russian mathematician and meteorologist named Alexander Friedmann who first showed that the equations of general relativity could describe a universe that was expanding or contracting in a perfectly natural way, without any need for the cosmological constant. In 1922, Friedmann published a paper in which he derived solutions to Einstein's field equations that described universes of varying curvature, some expanding forever, some destined to collapse back upon themselves, depending on the density of matter they contained. These were elegant and mathematically rigorous solutions, and they suggested that the universe might be a dynamic, evolving entity rather than a static backdrop. Einstein, upon reading Friedmann's work, was initially dismissive. He sent a note to the journal in which Friedmann had published, claiming to have found an error in the calculations, and he described the results as suspicious. Later, After corresponding with Friedman and reviewing the mathematics more carefully, Einstein acknowledged that there was no error, that Friedman's solutions were correct, though he still did not believe they had any physical relevance to the actual universe in which we live. It was a rare misstep for Einstein, and one that he would later come to regret, for Friedman's expanding universe models turned out to be a far more accurate description of reality than the static universe Einstein had tried so hard to preserve. The observational confirmation of this expansion came in the late 1920s, through the work of the American astronomer Edwin Hubble, who was working at the Mount Wilson Observatory in California. Hubble observed that the light from distant galaxies was shifted toward the red end of the spectrum, a phenomenon known as redshift, and that the amount of this shift was proportional to the distance of the galaxy from us. The farther away a galaxy was, the faster it appeared to be receding. This relationship, which we now call Hubble's law, was precisely what one would expect if the universe were expanding in the manner Friedman had described. The space between us and the distant galaxies was stretching, and this stretching was causing the light from those galaxies to be stretched as well, shifting its wavelength toward the red. Hubble's observations provided the first direct evidence that we live in an expanding universe, and they set the stage for the development of modern cosmology. The rate at which the universe is expanding is quantified by a number known as the Hubble constant, which is usually expressed in units of kilometers per second per megaparsec. A megaparsec is a unit of distance equal to about 3.26 million light-years, and the Hubble constant tells us how much faster a galaxy appears to be receding for each additional megaparsec of distance between us and it. The current best estimates of the Hubble constant place it at approximately 70 kilometers per second per megaparsec, which means that for every megaparsec of distance, the recession velocity increases by about 70 kilometers per second. However, there is at present some disagreement among cosmologists about the precise value of this constant. Measurements made using observations of the cosmic microwave background, which we shall discuss shortly, suggest a value of about 67 kilometers per second per megaparsec, while measurements made using observations of nearby supernovae and other astronomical objects suggest a somewhat higher value, around 73 kilometers per second per megaparsec. This discrepancy, which has been called the Hubble tension, is a topic of ongoing research and debate, and it may indicate that our understanding of the universe is incomplete in some way, or it may simply reflect systematic errors in one or more of the measurement techniques. Either way, it is a reminder that cosmology, like all sciences, is a work in progress, a slow and patient accumulation of knowledge that proceeds by fits and starts, by small corrections and occasional surprises. One of the more sobering implications of the expansion of space is the existence of what is called the cosmological horizon, sometimes also referred to as the particle horizon or the observable universe limit. Because the universe is expanding, and because it has been expanding for a finite amount of time, there is a limit to how far we can see. Light travels at a fixed speed, approximately 300,000 kilometers per second, and it has had only 13.8 billion years since the beginning of the universe to reach us. One might therefore expect that the farthest objects we can see would be about 13.8 billion light-years away. But in fact, the situation is more complicated than that. Because the universe has been expanding all the while that the light has been traveling toward us. The space through which the light has been moving has itself been stretching. And as a result, the objects that emitted that light are now much farther away than they were when the light set out. The current radius of the observable universe is estimated to be about 46 billion light-years, and objects beyond this distance are, in a very real sense, unreachable. The light from those objects has not had time to reach us, and because the expansion of space is carrying them away from us faster than the speed of light, their light never will reach us. They are beyond our cosmological horizon, forever hidden from our view, and no signal or message or traveler could ever bridge the gap between us. Perhaps the most compelling evidence for the expansion of space, and for the hot, dense state from which the universe emerged, comes from the cosmic microwave background, a faint glow of radiation that permeates all of space, and that was first detected in the year 1965 by two radio astronomers named Arno Penzias and Robert Wilson. Penzias and Wilson were working at the Bell Telephone Laboratories in Holmdel, New Jersey, using a large horn-shaped antenna that had originally been built for satellite communication experiments. They were attempting to measure the radio emissions from the Milky Way galaxy, and they encountered a persistent background noise that they could not account for. The noise was isotropic, meaning it came from all directions equally, and it did not vary with the time of day or the season of the year. Penzias and Wilson were meticulous scientists, and they made every effort to identify and eliminate possible sources of interference. They even discovered that pigeons had been nesting inside the horn of the antenna and had left behind what the scientists delicately described as a white dielectric material, which is to say, pigeon droppings, and they carefully cleaned the antenna and removed the pigeons. But the mysterious noise persisted. It was only when Penzias and Wilson learned of theoretical work being done by a group of cosmologists at nearby Princeton University that the true nature of the noise became clear. The Princeton group, led by Robert Dicke, had predicted that if the universe had begun in a hot, dense state and had been expanding and cooling ever since, then there should be a residual glow of thermal radiation left over from the early universe, a kind of cosmic afterglow that would now be visible as microwave radiation filling all of space. Penzias and Wilson had inadvertently discovered this radiation, and their discovery provided stunning confirmation of the Big Bang model of cosmology. They were awarded the Nobel Prize in Physics in 1978 for their work. The cosmic microwave background has since been studied in exquisite detail by a succession of satellite missions and ground-based experiments, and it has yielded a wealth of information about the early universe. The radiation has a nearly perfect blackbody spectrum, which is the spectrum of thermal radiation emitted by an object in equilibrium with its surroundings, and its temperature has been measured to be approximately 2.725 Kelvin, which is to say about 2.725 degrees above absolute zero. This is extraordinarily cold by everyday standards, but it is exactly what one would expect if the universe had begun in a hot, dense state some 13.8 billion years ago and had been expanding and cooling ever since. The light that we now detect as the cosmic microwave background was emitted when the universe was only about 380,000 years old, at a time when the cosmos had cooled enough for neutral atoms to form and for light to travel freely through space for the first time. That light has been traveling toward us ever since, and during its long journey, the expansion of space has stretched its wavelength by a factor of more than 1,000, shifting it from the visible and infrared into the microwave portion of the electromagnetic spectrum. And so, when you look up at the night sky, you are looking out into a universe that is gently, inexorably stretching, carrying the galaxies along with it like raisins in a rising loaf of bread. The evidence for this stretching is written in the redshift of distant galaxies, in the faint glow of the cosmic microwave background, in the elegant mathematics of general relativity and the careful observations of generations of astronomers. It is a slow process, unfolding on timescales that dwarf the span of a human life, and it is happening right now, in the quiet spaces between the stars, in the vast and patient reaches of intergalactic space. And there is something strangely soothing in that, something reassuring in the knowledge that the universe is not static, not frozen, but gently evolving, gently changing, gently carrying all things along with it into an unknown but unhurried future. In the late 1990s, two separate groups of astronomers set out to measure something they believed they already understood, at least in its general shape, and what they found instead would quietly overturn nearly everything we thought we knew about the fate of the universe. Though at the time, in the careful way of science, they simply called it an unexpected result and went back to check their instruments, their calculations, their assumptions, and then, finding nothing wrong, they checked them all again. The year was 1998, and the question these researchers hoped to answer was, in a sense, rather simple, the kind of question you might ask about a ball thrown into the air, which is to say, how quickly is the universe slowing down? Because it seemed obvious that it must be slowing down, that the expansion which had been ongoing since the beginning of time would naturally be losing momentum as gravity, that gentle and persistent force, pulled everything back toward everything else. And so these teams of astronomers pointed their telescopes at very distant supernovae, those brilliant explosions that mark the death of certain stars, and they measured how far away these supernovae were and how fast they were receding, expecting to find that the most distant ones were moving a bit more slowly than the nearer ones, as they should be if the expansion were winding down like a spinning top, gradually losing its energy. The first of these two groups was known as the Supernova Cosmology Project, and it was based at the Lawrence Berkeley National Laboratory in California, led by a physicist named Saul Perlmutter, who had been working on this problem since the late 1980s, developing methods to find supernovae reliably and in sufficient numbers to make meaningful measurements, which had previously been quite difficult because supernovae are unpredictable events, and you cannot simply schedule your telescope time around them. So Perlmutter and his colleagues devised a way of scanning large portions of the sky and comparing images taken weeks apart to catch new supernovae just as they were brightening. A methodical approach that took years to refine, but eventually proved remarkably successful. The second group called themselves the High Z Supernova Search Team, where the Z refers to redshift, a measure of how much the light from distant objects has been stretched by the expansion of space. And this team was led by Brian Schmidt, an American-born astronomer working in Australia, along with Adam Rees, who at the time was a young postdoctoral researcher at Berkeley, just down the road from Perlmutter's group. Though the two teams worked separately and, in the manner of scientific competition, each hoped to publish their results first, to be the ones who pinned down the precise rate at which cosmic expansion was decelerating, a measurement that would tell us something profound about the ultimate fate of everything. Now, to understand what these astronomers were doing, it helps to know a little about the particular type of supernova they were studying, which is called a Type Ia supernova. And these explosions have a very special property that makes them extraordinarily useful for measuring cosmic distances, which is that they all release very nearly the same amount of light, making them what astronomers call standard candles, a term borrowed from the days when actual candles of known brightness were used to calibrate the sensitivity of photographic instruments. And the reason Type Ia supernovae are so consistent is that they all arise from the same basic process in which a white dwarf star, the dense remnant of a sun-like star that has exhausted its fuel, accumulates matter from a companion star until it reaches a critical mass, about 1.4 times the mass of our Sun, at which point it can no longer support itself against its own gravity and undergoes a runaway thermonuclear explosion. And because this critical mass is always the same, the explosion is always of approximately the same power, reaching a peak brightness about 5 billion times greater than our Sun, bright enough to be seen across truly staggering distances. By measuring how bright a Type Ia supernova appears to us here on Earth, and knowing how bright it actually is, astronomers can calculate how far away it is, in much the same way you might judge the distance of a car at night by how dim its headlights appear, assuming you know how bright headlights are supposed to be. And this technique works even when the supernovae are so far away that their light has been traveling toward us for billions of years, which means we are seeing them not as they are now, but as they were in the distant past, when the universe was younger and smaller. And this is precisely why these observations are so valuable, because they let us measure how the rate of expansion has changed over cosmic time, comparing the expansion then to the expansion now. Among the many supernovae observed by these teams was one designated SN 1997 AP, discovered in early 1997 in a galaxy so far away that its light had been traveling for roughly 2/3 of the age of the universe. And this particular supernova, along with dozens of others collected over several years of patient observation, would contribute to a result that neither team expected and that both teams, working independently, confirmed. What they found was that the distant supernovae were dimmer than they should have been, not by a large amount, by a measurable amount, dimmer than they would be if the expansion of the universe were slowing down, and dimmer even than they would be if the expansion were proceeding at a constant rate. And the only explanation that fit the data was that the expansion of the universe is not slowing down at all, but is in fact speeding up, that the most distant galaxies are receding from us faster than expected, and that this acceleration has been going on for several billion years. A discovery, so, contrary to expectations, that both teams spent considerable time trying to find errors in their work, alternative explanations that might account for the dimness of the distant supernovae without requiring such a dramatic revision of our understanding. Perhaps, they wondered, the supernovae themselves were different in the early universe, less luminous for some reason related to the younger age of their host galaxies. But detailed analysis of the light from these explosions showed no evidence of such differences. Perhaps there was dust between us and the distant supernovae, absorbing some of their light and making them appear dimmer. But dust has a characteristic signature, reddening the light that passes through it in a particular way. And this signature was not present in the observations. Perhaps there was some systematic error in the way the distances were being calculated, some flaw in the assumptions underlying the standard candle method. But when the two rival teams compared their results, working with different telescopes, different analysis techniques, and different supernovae, they found that they agreed, and that agreement, between competitors who had every incentive to find flaws in each other's work, was perhaps the most convincing evidence of all. The rivalry between these two groups, which had been quite real and at times quite intense, gradually gave way to a shared recognition that they had stumbled upon something genuine and profound. And in 1998, both teams published their findings, separately but simultaneously, announcing to the world that the expansion of the universe is accelerating, and that something must be causing this acceleration. Some form of energy that pushes outward rather than pulling inward, counteracting and indeed overwhelming the attractive force of gravity on the largest scales. This mysterious something came to be called dark energy, a name chosen partly because we cannot see it, as it neither emits nor absorbs light, and partly because we do not understand what it is. And current measurements indicate that dark energy accounts for approximately 68% of the total energy content of the universe, making it by far the dominant component, more abundant than ordinary matter, which makes up only about 5%, and more abundant even than dark matter, that other mysterious substance which accounts for about 27% and which holds galaxies together, but which is itself invisible and poorly understood. And so we find ourselves in the rather humbling position of knowing that the universe is made mostly of things we cannot see and do not comprehend, with the familiar matter of planets and stars and human bodies constituting only a small fraction of the whole. What dark energy actually is remains one of the deepest unsolved problems in physics, and there are several possibilities that scientists have considered, the simplest being that it is a property of space itself, that empty space is not truly empty, but contains a small amount of energy in every cubic centimeter, and that this energy has the peculiar property of causing space to expand, which in turn creates more space, which contains more energy, which causes more expansion, in a self-reinforcing process that will continue indefinitely into the future. This idea that empty space might have an intrinsic energy is not a new one. And in fact, it traces back to Albert Einstein, who in 1917 introduced a term into his equations of general relativity that he called the cosmological constant, a mathematical device that represented a kind of repulsive force built into the fabric of space itself. And Einstein added this term for a specific reason, which was that at the time the universe was believed to be static, neither expanding nor contracting. And without the cosmological constant, his equations predicted that gravity would cause the universe to collapse in on itself. So he included this extra term to balance gravity and keep the cosmos stable, though he was never entirely happy with it, finding it inelegant and arbitrary. Then, In 1929, Edwin Hubble discovered that distant galaxies are moving away from us and that the universe is in fact expanding. And suddenly, there was no need for the cosmological constant. The universe was not static after all. And Einstein reportedly called the cosmological constant his biggest blunder, embarrassed that he had introduced this artificial term to preserve a static universe that did not exist. And for decades afterward, the cosmological constant was largely forgotten, a historical curiosity from the early days of relativistic cosmology. But the discovery of cosmic acceleration in 1998 suggested that Einstein may have been right after all, though for the wrong reasons, and that the cosmological constants, or something very much like it, does exist and is responsible for pushing the universe apart at an ever-increasing rate, which would mean that Einstein's blunder was not a blunder at all, but an insight ahead of its time, a possibility that I imagine would have given him complicated feelings, pride, perhaps mixed with frustration, that he had abandoned the idea too quickly. In the years following the initial discovery, additional evidence for cosmic acceleration accumulated from independent sources, most notably from detailed measurements of the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills the sky in all directions, and two satellite missions in particular. The Wilkinson Microwave Anisotropy Probe, known as WMAP, launched in 2001, and the Planck satellite, launched in 2009, mapped this radiation with extraordinary precision and found patterns that confirmed the presence of dark energy in exactly the amounts suggested by the supernova observations. A beautiful concordance between completely different types of measurements that gave scientists confidence the result was real. In 2011, the Nobel Prize in Physics was awarded jointly to Saul Perlmutter, Brian Schmidt, and Adam Riess for their discovery of the accelerating expansion of the universe through observations of distant supernovae, a recognition of work that had fundamentally changed our understanding of cosmic history and cosmic destiny. And though the prize went to only 3 individuals, as Nobel Prizes must, it represented the efforts of many dozens of researchers on both teams who had contributed to the observations, the analysis, and the long process of convincing themselves and the scientific community that the result was genuine. And so we come to understand that the universe is not merely drifting apart, not merely expanding in the gentle way that a loaf of bread rises as it bakes, but is accelerating, speeding up, with distant galaxies receding from us faster and faster with each passing moment, carried away by an energy we cannot see and do not understand. And this acceleration means that in the far future, billions of years from now, the galaxies beyond our local group will have receded so far and so fast that their light will no longer reach us, and the sky will grow darker, and the universe will become a lonelier place. Though all of this will happen so slowly and so gently that no one who might exist then would notice it happening any more than we notice the slow drift of continents beneath our feet. And now we come to a quieter chapter of this cosmic story, one that unfolds not with the drama of collision or the violence of stellar explosion, but with something far more subtle, far more patient, and in its own way, far more profound, which is simply the gentle withdrawal of everything we might see, the slow retreat of the visible universe into a kind of perfect solitude that cosmologists sometimes call the Great Isolation. though they say it with the same calm detachment with which one might describe the eventual cooling of a cup of tea left too long on a windowsill. To understand what awaits the cosmos in the extraordinarily distant future, we must first consider what physicists mean when they speak of the observable universe, which is not quite the same thing as the universe itself. For the observable universe is simply that portion of all existence from which light has had sufficient time to reach us since the beginning of everything, a sphere of visibility centered on wherever you happen to be standing, or floating, or quietly existing. And this sphere has an edge, not a physical edge made of anything you could touch or see, but a horizon beyond which photons have not yet completed their journey to your eyes. And this horizon, this cosmic horizon, is not fixed in place, but is itself subject to the expansion of space, stretching and shifting in ways that depend upon how quickly the universe grows. In the year 2007, two physicists named Lawrence Krauss and Robert Scherer published a paper with the rather evocative title, The Return of a Static Universe. And in this paper, they performed a series of calculations that traced the fate of our cosmic horizon forward through time. Not merely millions or billions of years, but hundreds of billions of years, into epochs so distant that our present moment would seem as ancient to those future times as the first microsecond after the Big Bang seems to us. And what they found, through careful application of the mathematics of an accelerating cosmos, was something both beautiful and melancholy, which is that the universe we can see is slowly emptying, like a room from which guests are departing one by one, each stepping quietly through a door that closes behind them and cannot be reopened. You see, the expansion of the universe is not merely continuing, it is accelerating, driven by that mysterious presence we call dark energy, which fills all of space with a gentle but relentless outward pressure. And this acceleration means that distant galaxies are not simply moving away from us, they are moving away from us at ever-increasing speeds. And there comes a point, for each distant galaxy, when the rate of recession exceeds the speed of light itself, not because the galaxy is traveling through space faster than light, which would be forbidden, but because the space between us and that galaxy is stretching so quickly that light can no longer cross the growing gulf. And when this happens, that galaxy slips beyond our cosmic horizon, its light redshifted into longer and longer wavelengths, stretched thinner and thinner until it fades entirely from view, like a ship disappearing over the curve of an infinite ocean. Except that this ship will never return, and no message from it will ever reach our shores again. Krauss and Scherer calculated that in approximately 100 billion years from now, give or take the inevitable uncertainties in such distant projections, every galaxy beyond our own local neighborhood will have crossed this horizon, will have receded past the point of no return. And the sky, which currently contains hundreds of billions of galaxies scattered across the observable universe, each one a vast city of stars, will contain only the stars of our own merged galaxy, floating in what will appear to be an infinite and perfect darkness, a void without end, without feature, without any hint that anything else exists or ever existed. But our own galaxy, the Milky Way, will not exist in quite the same form that we know it today, for there is another process unfolding on a somewhat shorter timescale, which is the gravitational dance between our galaxy and our nearest large neighbor. the Andromeda Galaxy, which is sometimes called Messier 311, and which currently lies approximately 2.5 million light-years away. A distance so vast that the light reaching us from Andromeda tonight began its journey when our ancestors were just learning to chip stone tools. And yet, Andromeda is approaching us, moving toward the Milky Way at a speed of roughly 110 kilometers every second, which sounds quite fast, and indeed it is. Though at such tremendous distances, it amounts to a very slow and stately approach. A gravitational courtship that will culminate in approximately 4.5 billion years, when the two galaxies will begin to merge. This merger will not be the violent collision one might imagine, for galaxies are mostly empty space. The distances between individual stars so vast that the chances of any two stars actually colliding during the galactic merger are vanishingly small, almost negligible, like the probability of two gnats colliding if you release them in separate cathedrals and slowly push the cathedrals together. And so the stars will pass by one another, their orbits disrupted and rearranged by shifting gravitational fields, but the stars themselves remaining intact. And over the course of several billion years, the two spiraling disk galaxies will distort and stretch and eventually settle into a new configuration. A vast elliptical galaxy, a great spherical cloud of stars no longer organized into graceful spiral arms, but distributed more evenly, more smoothly, in what astronomers sometimes call a giant elliptical galaxy. And this future galaxy has been given several informal names, among them Milkdromeda, or sometimes Milkomeda, names that blend the identities of the two parent galaxies into something new, something that will be neither quite Milky Way nor quite Andromeda, but a child of both. Our local group, as astronomers call it, contains not just the Milky Way and Andromeda, but approximately 80 galaxies of various sizes. Most of them small dwarf galaxies, dim collections of stars that orbit their larger companions, like attendants around a great estate. And this entire group is bound together by gravity, the mutual attraction of all that mass holding the collection together against the expansion of space. And so, while distant galaxies recede and fade beyond the horizon, the local group will remain intact, its members drawing closer together over time, eventually merging into that single great elliptical galaxy. And this merged galaxy will be our island, our home, the entirety of the visible universe for any astronomers who might exist in that distant epoch. The physicist Freeman Dyson, who devoted considerable thought to the far future of the cosmos, wrote extensively about what existence might be like in these distant epochs, approaching the subject not with despair, but with a kind of calm curiosity, wondering what forms of life or intelligence might persist, what sources of energy might be harvested, what thoughts might be thought when the stars have dimmed and the universe has grown cold. And while Dyson's speculations ranged into territories of almost unimaginable strangeness, touching on questions of thermodynamics and information and the minimum energy required to process a single thought, one theme that emerges from his work is the importance of understanding not just where we are in the universe, but when, recognizing that the cosmos has a history, a past, a beginning, and that our present moment is not typical, but is rather a brief window, a fleeting era when the universe is neither too young to contain complex structures, nor too old to have lost the evidence of its own origins. And this brings us to what may be the most profound implication of the coming Great Isolation, which concerns not just what future observers will fail to see, but what they will fail to know. For among the things that will be lost beyond the cosmic horizon is the evidence of the Big Bang itself, the very signature of the universe's beginning, which we currently observe in the form of the cosmic microwave background radiation, that faint glow of ancient light that fills all of space, the afterglow of the moment when the universe first became transparent to light, roughly 380,000 years after the beginning of everything. This cosmic microwave background, sometimes called the CMB, is perhaps the most important piece of evidence we have for the Big Bang, a nearly uniform bath of microwave radiation coming from every direction in the sky, with tiny fluctuations in temperature that map the density variations in the early universe, the seeds from which all galaxies would eventually grow. And we can observe this radiation today because the photons that comprise it have been traveling towards us for over 13 billion years, stretched by the expansion of space from their original high-energy form into the much longer wavelengths of microwaves. And we have built instruments to detect this radiation. Satellites like COBE and WMAP and Planck, which have mapped its subtle patterns with exquisite precision, giving us a window into the infancy of the cosmos. But the expansion of the universe does not stop, and the stretching of these ancient photons continues. And as the expansion accelerates, the wavelength of the cosmic microwave background will grow longer and longer, redshifting from microwaves into radio waves, from radio waves into ever longer and lower frequency radiation, until eventually, in the far distant future, these photons will have been stretched so thin that their wavelength will exceed the size of the observable universe itself. And at that point, they will no longer be detectable by any means. They will have effectively vanished, leaving no trace behind, no echo, no whisper of the ancient fireball that marked the beginning of time. And so, a civilization arising in that distant epoch, inhabiting the merged elliptical galaxy that was once the Milky Way and Andromeda, looking out at the sky with whatever instruments they might devise, would see only their own galaxy, surrounded by perfect emptiness, and they would find no cosmic microwave background to hint at a hot, dense beginning. No distant galaxies receding in accordance with Hubble's law to suggest that space itself is expanding. No evidence whatsoever that the universe had ever been different from what they observe. A single island of stars floating in an infinite static void. These future astronomers, if they exist, might reasonably conclude that their galaxy is the entirety of existence, that the void surrounding them has always been void and will always remain, so that the universe is eternal and unchanging, precisely the view that astronomers on Earth held before Edwin Hubble's observations in the 1920s revealed the expansion of space, and before the discovery of the cosmic microwave background in 1965 confirmed the Big Bang. And so the irony is complete, that the very expansion which revealed to us the dynamic history of the cosmos will, in time, erase the evidence of that history, will hide the truth of the universe's beginning from any minds that might come after, will return cosmology to a kind of ignorance from which we only recently emerged. There is something quietly poignant in this. The idea that our particular moment in cosmic history is special, not because we are special, not because there is anything unusual about our position in space, but because we happen to exist in an era when the universe is still willing to reveal its secrets, when the evidence of the Big Bang is still written across the sky for anyone with the right instruments to read. And this window of revelation will not remain open forever. Indeed, on cosmic timescales, it will close relatively soon. And what will remain is simply the merged galaxy, the gathered stars of the local group, shining in a darkness that contains no memory of what came before. The Great Isolation, then, is not merely a physical separation, though it is certainly that, but also a kind of epistemic isolation, a closing off of knowledge, a drawing of curtains across the windows of the universe. And those who come after, if any do, will be left with a cosmos that reveals nothing of its own past, that offers no clues to its own origin, that presents itself as eternal and static and alone. And whether this is a tragedy or simply a fact depends very much on your perspective. Though from where we sit now, with the cosmic microwave background still glowing faintly all around us, and the distant galaxies still visible in our telescopes, it seems worth noting, worth appreciating, that we live in a time when the universe is still telling its story, still offering its evidence, still allowing us to piece together the remarkable history of everything that has ever been. So we come now to the part of our exploration where we sit quietly with uncertainty, where we let the not knowing rest gently upon us like a soft blanket, and we consider the various ideas that careful minds have put forward to explain this peculiar force that is pushing the universe apart. These are not wild guesses thrown hastily at a problem, but rather thoughtful proposals built upon decades of mathematical reasoning and observational work, each one attempting to account for what we see when we look out into the deep and expanding cosmos. None of them is proven beyond doubt, and perhaps that is part of what makes this a good topic for these quiet hours, because there is something restful in acknowledging that even the most brilliant among us are still wandering through possibilities, still gathering evidence, still piecing together clues scattered across billions of light years. The most straightforward explanation, and the one that many cosmologists have settled into as a kind of working hypothesis, is what we call the cosmological constant, which has a rather interesting history of its own. Albert Einstein first introduced this concept in 1917, not because he had observed accelerating expansion, but rather because he wished to prevent expansion altogether, to hold the universe in a static and unchanging state that matched the assumptions of his time. He added a term to his equations of general relativity, a small, positive constant that would act as a kind of repulsive pressure, counterbalancing the attractive pull of gravity and keeping everything in place. When Edwin Hubble later discovered that the universe was indeed expanding, Einstein reportedly considered this cosmological constant his greatest mistake, and he removed it from his equations. But decades later, when observations revealed not merely expansion, but accelerating expansion, the cosmological constant returned, rehabilitated and reinterpreted, no longer a mistake, but perhaps a profound insight arrived at for the wrong reasons. In its modern form, the cosmological constant is understood as something called vacuum energy, which is the energy inherent in empty space itself. in the quantum fields that permeate every corner of the cosmos, even where no matter exists. According to quantum mechanics, what we perceive as empty space is not truly empty at all, but rather a seething foam of virtual particles flickering in and out of existence, borrowing energy from the vacuum for brief moments before returning it. And all of this activity contributes a baseline energy to the fabric of space-time. This energy, if it behaves in the right way, would create exactly the kind of negative pressure, the repulsive effect, that could drive cosmic acceleration. It is an elegant idea, connecting the very large with the very small, linking the fate of galaxies to the quantum behavior of the tiniest constituents of reality. But here is where things become troubling, and also perhaps a little amusing in the way that physics can sometimes be when its predictions go spectacularly wrong. When theoretical physicists sat down to calculate how much vacuum energy there should be, adding up the contributions from all the quantum fields and their virtual fluctuations, they arrived at a number so large that it defies comprehension. The calculated value exceeds the observed value by a factor of roughly 10 to the power of 120, which is a 1 followed by 120 zeros. To put this in some perspective, if you were off by that much in calculating the amount of petrol needed to drive to the shops, you would have estimated enough fuel to power every car on Earth for longer than the universe has existed, multiplied by itself more times than there are atoms in the observable cosmos. It has been called, with dry understatement characteristic of physicists, the worst prediction in the history of physics. Something is clearly missing from our understanding. Some mechanism that cancels out nearly all of this vacuum energy while leaving just the faint residue that we actually observe. What that mechanism might be remains unknown. And so, even the cosmological constant, our simplest and most popular explanation, carries within it a profound and unresolved mystery. Perhaps, then, dark energy is not a constant at all. Perhaps it is something that changes and evolves as the universe ages, something dynamic rather than static, a field that shifts its behavior over cosmic time. This possibility has been given the name quintessence, a word borrowed from ancient philosophy, from the writings of Aristotle, who believed that while the terrestrial world was made of 4 elements, earth and water and air and fire, the heavens were composed of something different, a 5th essence, a pure and unchanging substance that made up the stars and planets. The modern quintessence is not quite the same as Aristotle's vision, but the name captures something of its spirit. A 5th component of the cosmos alongside ordinary matter and radiation and dark matter, something subtle and pervading that fills all of space. In quintessence theories, dark energy is a quantum field, sometimes called a scalar field, that has a particular energy associated with it at each point in space. And this energy can change over time as the field slowly rolls down its potential, somewhat like a ball rolling down a very gentle hill, so slowly that you can barely perceive its motion. The rate at which it rolls, and the shape of the hill it is rolling down, would determine how the cosmic acceleration changes over the history of the universe. In some versions of quintessence, dark energy might have been weaker in the past and is growing stronger now. In other versions, it might eventually weaken and fade away, allowing gravity to reassert its dominance in the distant future. The universe might not continue accelerating forever, but might slow down again, or even begin to contract. These possibilities depend on the details of the quintessence field, on parameters we do not yet know, and so testing whether dark energy is truly constant or whether it varies with time has become one of the most important goals of modern observational cosmology. To answer such questions, we must gather data, enormous quantities of it, from the farthest reaches of the observable universe. And so, humanity has built, and continues to build, instruments of remarkable precision and ambition. Telescopes that peer back through billions of years of cosmic history, mapping the positions and distances of countless galaxies, measuring the subtle patterns that dark energy has imprinted upon the large-scale structure of the cosmos. One such endeavor is the Dark Energy Survey, which has been operating since 2013 using the Victor M. Blanco telescope high in the mountains of Chile, at the Cerro Tololo Inter-American Observatory, where the air is thin and dry and the skies are dark and clear. Over the course of 6 years of observations, this survey mapped the positions, shapes, and colors of more than 300 million galaxies, creating a census of the cosmic web across an enormous volume of space. By measuring how light from distant galaxies is bent and distorted by the gravitational influence of matter along its path, a technique called weak gravitational lensing, the survey has mapped the distribution of both ordinary and dark matter throughout the universe. By comparing these maps at different cosmic epochs, at different distances, and therefore different ages, researchers can trace how the growth of cosmic structure has been affected by dark energy over billions of years. Joining this effort from space is the Euclid telescope, a mission developed by the European Space Agency and launched in July of 2023. Euclid was designed specifically to study dark energy and dark matter, carrying instruments optimized for precisely the kinds of measurements needed to constrain the nature of cosmic acceleration. From its position at the second Lagrange point, about 1.5 million kilometers from Earth, where it is shielded from the planet's heat and light, Euclid is surveying more than 1/3 of the sky, imaging billions of galaxies out to distances corresponding to 10 billion years of look-back time. Its goal is to measure the expansion history of the universe and the growth of cosmic structure with unprecedented precision, to distinguish between a true cosmological constant and a dynamic quintessence field, to narrow down the possibilities and guide us toward understanding. Looking ahead, the Vera C. Rubin Observatory is expected to come online in 2025, perched atop Cerro Pacon in Chile, another mountain carefully chosen for its excellent astronomical conditions. This observatory is named in honor of Vera Rubin, the American astronomer whose meticulous observations of galaxy rotation curves provided some of the most compelling evidence for dark matter, demonstrating that galaxies contain far more mass than can be accounted for by their visible stars. It is fitting that a telescope bearing her name will contribute to understanding dark energy, the other great cosmic mystery that complements the dark matter she helped reveal. The Rubin Observatory will conduct the Legacy Survey of Space and Time, imaging the entire visible southern sky repeatedly over 10 years, tracking how objects move and change, detecting transient events like supernovae that can serve as distance indicators for measuring cosmic expansion, building up an unprecedented database of cosmic information. Meanwhile, the Dark Energy Spectroscopic Instrument, known by its abbreviation DESI, has been operating at the Kitt Peak National Observatory in Arizona, engaged in an ambitious campaign to create the largest three-dimensional map of the universe ever constructed. DESI works by measuring the spectra of galaxies and quasars, splitting their light into component wavelengths to determine precisely how much that light has been stretched by cosmic expansion, how much redshift each object exhibits, and therefore how far away it lies and how fast it is receding. By the time its survey is complete, DESI will have measured the redshifts of more than 35 million galaxies and quasars, providing a detailed map of how matter is distributed across cosmic time, how the patterns of clustering have evolved as dark energy has pushed space apart. Among the scientists working to interpret all of this data is Adam Rees, whom we mentioned earlier as one of the co-discoverers of cosmic acceleration. He has continued his work in the decades since that initial discovery, refining and improving the measurements of the cosmic expansion rate, using the Hubble Space Telescope and more recently the James Webb Space Telescope to observe Cepheid variable stars and Type Ia supernovae with ever greater precision. His efforts have revealed what some call the Hubble tension, a discrepancy between the expansion rate measured from the nearby universe and the rate inferred from the cosmic microwave background radiation left over from the early universe. Whether this tension indicates something unexpected about dark energy, or some systematic error in the measurements, or something else entirely about our cosmological models, remains to be determined. It is one more piece of the puzzle, one more clue that we are still assembling, one more reason why the observations continue. There are also those who wonder whether dark energy exists at all, whether perhaps what we are interpreting as a mysterious repulsive energy is actually a signal that our understanding of gravity itself is incomplete. Einstein's general relativity has passed every test we have devised for it, from the bending of starlight around the sun to the detection of gravitational waves from colliding black holes. But all of these tests have been conducted in relatively strong gravitational fields or over relatively short distances, perhaps on the largest scales, across the vast emptiness between galaxy clusters where gravity is extraordinarily weak. The rules are somehow different. One proposal along these lines is called modified Newtonian dynamics, or MENY, which was originally developed to explain the rotation curves of galaxies without invoking dark matter. While MOND, in its original form, does not easily account for cosmic acceleration, it has inspired more sophisticated modified gravity theories that attempt to explain both dark matter and dark energy as manifestations of gravity behaving differently than Einstein predicted. These theories are mathematically complex and face significant challenges in matching all of the observational data. But they remain active areas of research, possibilities that have not been ruled out. And so we find ourselves in a curious position, possessing extraordinary tools and accumulating astonishing quantities of data, mapping hundreds of millions of galaxies, measuring the expansion rate with percent-level precision, yet still uncertain about the fundamental nature of the force that dominates the cosmos. We are gathering light from the most distant objects visible, light that has traveled for billions of years before reaching our instruments, and we are using that ancient light to solve a mystery written across all of space, a mystery that concerns the fate of everything that exists. There is something quietly magnificent about this endeavor, about the patience required to collect photons one by one over years of careful observation, about the willingness to follow the evidence wherever it leads, even into territory that seems strange and unfamiliar. The answer may be the cosmological constant, after all, a simple number woven into the fabric of space-time. Or it may be quintessence, a dynamic field that is still evolving even now. Or it may be something we have not yet imagined, something that will require new physics and new insights to understand. For now, we wander through the possibilities, considering each one carefully, weighing the evidence, waiting for the data to guide us toward clarity. And that is perhaps not such a bad way to spend one's time, wandering thoughtfully through a landscape of ideas, patient and unhurried, letting understanding come in its own good time. And so we return now, gently, to where we began, which is to say, we return to you, lying perhaps on a blanket spread across grass that is cool with evening dew, or resting against a pillow positioned near a window, or simply closing your eyes and imagining a night sky so filled with stars that it seems impossible such darkness could hold so much light. This is the personal scale of things, the human scale, the scale at which you can feel the solid earth beneath you and the soft rhythm of your own breathing, and yet also sense, if you let your mind drift just slightly upward, that you are part of something so vast that the words we have for vastness begin to seem rather small. The stars you see tonight, those pinpricks of ancient fire scattered across the dome of sky, are genuinely drifting away from you. This is true. The expansion we have spoken of, that patient stretching of space itself, is happening even now, even as you breathe, even as you listen to these words. And yet it is happening so slowly, so impossibly gently, that if we could somehow freeze your exact position in the cosmos and wait for 10,000 human generations to live and love and wonder at the same sky, those distant descendants would notice nothing different at all. The stars would appear to hang in precisely the same positions, the constellations would hold their familiar shapes, and the great river of the Milky Way would still arc overhead in that same luminous band that has inspired every civilization that ever tilted its collective face toward night. 10,000 generations is rather a long time by human reckoning, long enough for languages to be born and to die and to be forgotten entirely, long enough for continents to shift by meters that would be imperceptible to any single lifetime. And yet, even across all that patient accumulation of years, the cosmic drift would remain essentially invisible to any eye looking up from Earth. This is one of the quiet kindnesses of scale, that the universe can be expanding at every point, stretching in that gentle way we have described. And yet, the stars of your familiar sky remain yours for as long as humanity is likely to exist. The patterns that the ancient Greeks named for their heroes and monsters, the patterns that navigators used to cross dark oceans, the patterns that you perhaps learned as a child lying in summer grass, much like you might be lying now. These patterns are stable on timescales that dwarf everything we call history. The expansion is real, but it is patient, and it does not ask you to notice it happening. There is something else worth knowing as you lie beneath these stars. Something that might seem to contradict everything we have discussed, but which actually illuminates a rather lovely exception to the general rule. The nearest large galaxy to our own, a great spiral collection of several 100 billion stars that we call Andromeda, is not drifting away from us at all. It is, in fact, approaching, at this very moment, as you rest and breathe and let your thoughts wander towards sleep. The Andromeda Galaxy is moving toward the Milky Way at approximately 110 kilometers every second, which is to say, it is swimming against the cosmic current, pulled by the mutual gravity that our two galaxies have exerted on each other since both were young. This is not a contradiction of expansion, but rather a testament to the power of local gravity to override the general stretching of space, at least within certain neighborhoods of the cosmos. Andromeda and the Milky Way are close enough, in galactic terms, that they feel each other's pull, that they are bound together by the same force that keeps your feet on the ground and the moon in its orbit and the Earth circling the Sun. Approximately 4.5 billion years from now, these two great spirals will meet, will pass through each other in a slow dance of gravitational interaction that will last millions of years, will eventually merge into a single larger galaxy that some astronomers have already named Milkomeda. Though of course, there will be no one using that name by then, at least not in any form we would recognize. But tonight, Andromeda is simply a faint smudge of light in the constellation that bears the name of a princess from Greek mythology, visible to the unaided eye on clear, dark nights, requiring no telescopes, only patience and a willingness to let your vision adjust to the darkness. If you can see it, you are seeing light that left that galaxy approximately 2.5 million years ago, which means you are seeing Andromeda not as it is now, but as it was when our distant ancestors were still learning to shape stone tools on the plains of Africa. The light has been traveling through the expanding void all that time, and yet here it is, arriving at your eyes, a message from across an almost incomprehensible distance, swimming toward you against the current of cosmic expansion. And this brings us to something worth sitting with for a moment, or rather, lying with, in that comfortable position you have found. The starlight touching your eyes tonight, the photons that are even now triggering tiny chemical reactions in the cells of your retina, began their journeys at times scattered across an enormous range of the past. The light from Proxima Centauri, our nearest stellar neighbor, departed just over 4 years ago. The light from Vega, that bright star in the constellation Lyra, has been traveling for about 25 years. The light from Polaris, N, the North Star that has guided so many travelers, left that star more than 400 years ago, around the time that Galileo was first turning his telescope toward the heavens, and the light from stars you can barely see, those faint glimmers at the edge of naked eye visibility, may have been traveling for thousands of years, may have departed when the pyramids were being built, or when the last ice age was still releasing its grip on northern continents. You are, in a very real sense, a collector of ancient light. The sky above you is a kind of museum of the past, with each point of light representing a different moment in cosmic history. all arriving simultaneously at this single moment of your perception, this quiet night, this gentle breath. The universe has been sending these messages for all that time, not caring whether anyone would be there to receive them, and yet here you are, receiving them, a temporary arrangement of matter that has somehow developed the capacity to wonder at the light of distant suns. The astronomer and writer Carl Sagan once reflected on this cosmic perspective in a way that has stayed with many who have read his words. He was contemplating a photograph of Earth taken by the Voyager 1 spacecraft from a distance of about 6 billion kilometers, a photograph in which our entire planet appears as a tiny pale blue dot, barely a pixel in size, suspended in a beam of scattered sunlight. In his reflection on this image, Sagan noted that everyone you have ever heard of, every human being who ever lived out their lives on that tiny speck. All our wars and all our loves, all our triumphs and failures, all the kings and peasants, all the young couples in love, all the mothers and fathers, all the children playing in the dust of ancient cities, all of it happened there, on a mote of dust suspended in a sunbeam. This was not, for Sagan, a diminishing observation, though it might seem so at first. It was rather an invitation to a kind of humility and wonder that he believed could make us kinder, could make us more aware of our responsibility to deal more gently with one another, to preserve and cherish what he called the only home we have ever known. The vastness of space, in this view, does not make our lives meaningless, but rather makes them precious, makes each act of love and connection and understanding something worth protecting in a cosmos that is mostly empty, mostly dark, mostly cold. That same Voyager 1 spacecraft, the one that took that famous photograph, is still out there. It is now approximately 24 billion kilometers from Earth, which is so far that radio signals traveling at the speed of light take more than 22 hours to make the journey in each direction. When engineers at NASA send a command to Voyager, they must wait nearly 2 days to learn whether the command was received and executed. The spacecraft is traveling at about 17 kilometers per second, heading outward into interstellar space, into the void between the stars, into the expanding universe that will carry it farther and farther from home with every passing moment. And on that spacecraft, attached to its side, is a golden phonograph record. This record contains greetings in 55 human languages, from ancient Sumerian to modern Wu Chinese, from Akkadian to Welsh. It contains the sounds of earth, thunder and wind and birdsong and whale calls, and the crash of surf. It contains music from around the world, Bach and Beethoven and Chuck Berry, and traditional songs from cultures spanning the globe. It contains encoded images of life on Earth, of animals and plants and human beings, of our mathematics and our biology and our place in the solar system. It is, in essence, a message in a bottle, thrown into an ocean that stretches for billions of light years in every direction, an ocean that is expanding even as the bottle drifts outward into it. The odds that any other intelligence will ever find the Voyager record are, by most reasonable estimates, extraordinarily small. The spacecraft is heading toward no particular star, and even if it were, the nearest stars are so far apart that Voyager will take tens of thousands of years to pass through the region of space that is merely nearby. Cosmically speaking, the record may drift through the galaxy for millions of years, for billions of years, without ever being found, without its greetings ever being heard. And yet, we sent it. We gathered together the sounds and images and music that we thought might represent us to some unknown listener in the cosmic dark, and we sent them outward, a gesture of hope into the expanding void. There is something rather beautiful in that gesture, something that speaks to the human need to reach out, to connect, to believe that we are not entirely alone in the vastness. The record carries its message in the language of science and mathematics, in the universal truths of physics and chemistry, and it carries also our art, our music, the sounds of our children laughing and our waves breaking on shores. It is a message that says, we were here. We noticed the universe. We wondered at it. We sent this small thing outward to say hello. Astronauts who have traveled to space and looked back at Earth often report an experience that has come to be called the overview effect. This is a cognitive shift, a change in awareness that many describe as profound and lasting. Looking down at the thin, bright curve of the atmosphere, seeing the fragile blue-white sphere of our planet against the absolute black of space, they often feel a sense of the interconnectedness of all life, a sense that the boundaries and conflicts that seem so important from the surface are revealed as small and temporary against the background of the cosmos. They describe a feeling of awe, yes, but also of responsibility, a recognition that the planet is finite and precious, and that we are all passengers together on this small ship moving through the dark. This experience of overview, of seeing oneself and one's home from the cosmic perspective, is perhaps something we can approximate even while lying on the ground beneath familiar stars. We can imagine the great distance from which those stars are shining, can imagine the Earth as it would appear from their vantage point, if any vantage point existed there. A tiny world circling an ordinary yellow star in an outer arm of an ordinary spiral galaxy. We can imagine ourselves as the universe looking back at itself, matter that has arranged itself in such a way as to contemplate its own existence, to wonder at the expansion that carries it forward, to feel both small and connected at the same time. The expansion of the universe means that certain futures are no longer possible. There was a time, in the early decades of cosmology, when scientists debated whether the universe might eventually stop expanding and collapse back in on itself, drawn together by the mutual gravity of all its matter, ending in a kind of reverse of the Big Bang, a big crunch that would bring everything back to a single point. But the observations of the past few decades have ruled out this possibility. The expansion is not slowing down, but rather speeding up, driven by dark energy. And this means the universe will never collapse. It will simply, gently, eternally stretch. This is the future that awaits the cosmos. Not a dramatic ending, but an endless continuation. An infinite stretching outward. A slow cooling as stars exhaust their fuel over trillions of years. As galaxies drift beyond each other's horizons, as the universe becomes ever more diffuse and quiet and cold. It is not a violent end, but a gentle one, if indeed it can be called an end at all. It is simply the universe continuing to do what it has always done, which is to expand, to stretch, to give everything more room, forever. And yet, here you are, in this small window of cosmic time, when stars still shine, and planets still orbit, and life still rises and falls and wanders at the sky. The expansion that will eventually spread everything into darkness is the same expansion that has given the universe time and space for galaxies to form, for stars to burn, for heavy elements to be forged in stellar cores, for those elements to find their way into planets and ultimately into you. You are made of material that was once inside stars, that was fused in nuclear fires billions of years ago, and you are lying here now, temporary and aware, watching the ancient light arrive. So let yourself breathe, slowly, deeply, in rhythm with a universe that has been expanding since time began. That expansion is happening now, has been happening for nearly 14 billion years, and will continue happening for longer than any mind can comprehend. And in all that time, in all that stretching of space, the universe has managed to produce you, has managed to create a moment in which consciousness can exist, can wonder, can lie beneath the stars and think about the great slow drift that carries everything forward. You are held in that drift, just as the galaxies are, just as the golden record on Voyager is, just as every atom in your body is. You are part of the expansion, not separate from it, not left behind by it, but woven into its very fabric. And the expansion, for all its vastness, for all its patient inevitability, is gentle. It does not rush. It does not demand. It simply stretches, slowly, forever, holding you in its slow, patient drift toward forever. Let that drift carry you now, toward rest, toward sleep, toward whatever quiet awaits on the other side of this breathing moment. The stars will still be there when you wake, still sending their ancient light, still drifting in their patient dance, still part of the same expanding cosmos that has been your home since before you were born. Rest in that knowledge. Rest in that slow, patient drift. Rest